Today, August 7th, 2026, NASA just released information about Voyager 2 that almost nobody is discussing yet. If you care about what's happening at the very edge of human reach in space, subscribe right now, because what just happened with this spacecraft changes what we understand about interstellar space. Let me walk you through the full picture. Voyager 2 is currently more than 13 billion miles from Earth. Take a moment to consider that number, 13 billion miles. Traveling at the speed of light, a radio signal from NASA's Deep Space Network takes over 19 hours just to reach it. Then another 19 hours for any reply to come back. So when engineers send a command to this spacecraft, they wait almost 2 full days to learn whether it worked. And on August 4th, 2026, they learned that it did. NASA's Jet Propulsion Laboratory just confirmed the success of what the engineering team nicknamed the Big Bang, a risky, all-at-once power management overhaul performed on Voyager 2 that took months to plan and left zero room for error because failure would have meant losing another science instrument before the end of this year. Instead, the Big Bang succeeded. Voyager 2 now has enough power to keep 3 science instruments running in interstellar space for at least another year beyond what was previously possible. And those 3 instruments sit more than 13 billion miles away in an environment no human-made object had ever entered before. Voyager 1 crossed that boundary in 2012, measuring things about interstellar space that can't be measured any other way from anywhere else. That's what happened today. And to understand just how much it matters, you need to understand what Voyager 2 actually is, where it actually is, and what it's been discovering in the space between the stars that no one knew existed before it got there. Voyager 2 launched on August 20th, 1977, 17 days before its twin Voyager 1, which launched on September 5th of that same year. The reason Voyager 2 launched first, despite carrying the number 2, is that it was placed on a slower, longer trajectory designed to take advantage of a rare planetary alignment, letting it fly past Jupiter, Saturn, Uranus, and Neptune in a single mission. That alignment happens only once every 176 years. NASA called this path the Grand Tour. Voyager 1 was sent on a faster route covering only Jupiter and Saturn, but one that would get it to interstellar space sooner. Both probes were originally designed for a 5-year mission. Neither has ever stopped working. Voyager 2 is now nearly 49 years into a mission meant to last 5. It visited Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. To this day, it remains the only spacecraft in history to have flown past the ice giants Uranus and Neptune. Everything we know about those planets from direct, up-close observation comes from a spacecraft built in the early 1970s, launched before personal computers existed, and still operating today on a fraction of the power it started with. Power is the central issue that has defined the Voyager mission for years now. Both probes rely on radioisotope thermoelectric generators, devices that convert heat from the radioactive decay of plutonium-238 into electricity. They're essentially nuclear batteries. And when Voyager 2 launched in 1977, those generators produced around 470 watts. Every year since, as the plutonium keeps decaying, output has dropped by roughly 4 watts annually. Nearly half a century later, the power available to Voyager 2 is so limited that every single watt must be accounted for. The engineering team has spent years working through a carefully prioritized shutdown sequence, turning off heaters first, then backup systems, then science instruments one by one, each in an order agreed on by the science and engineering teams based on which instruments were still returning useful data from interstellar space versus which had essentially completed their scientific purpose after the planetary flybys ended in 1989. Voyager 2 originally carried 10 science instruments. By early 2026, through years of planned deactivations, only 3 remained active: the magnetometer, the plasma wave subsystem, and the cosmic ray subsystem. Without the Big Bang intervention JPL just confirmed as successful, the cosmic ray subsystem had been scheduled for shutdown before the end of 2026, which would have left Voyager 2 with just 2 instruments. The Big Bang has bought at least another year for all 3. So what exactly is the Big Bang? JPL engineers describe it as a simultaneous swap of power devices. The spacecraft had been using 3 heater devices to keep its thruster fuel lines from freezing, because if those lines freeze, the thrusters stop working, the antenna can no longer be pointed at Earth, and the mission ends permanently. The Big Bang switched off those 3 heaters and switched on 3 alternative devices that accomplished the same thermal management goal while consuming almost 10 watts less power overall. 10 watts might sound trivial, but for a spacecraft with razor-thin power margins losing 4 watts a year, 10 watts is a massive gain, enough to delay a science instrument shutdown by at least a year. The risk came from the precision required. The swap had to happen simultaneously, not in sequence. If the replacement thermal devices hadn't come online quickly enough after the heaters were cut, the fuel lines could have started cooling toward dangerous temperatures before protection was restored. Engineers tested the procedure on Voyager 2 during May and June 2026. Since Voyager 2 is closer to Earth than Voyager 1, meaning the 2-day command response cycle is slightly shorter, and because Voyager 2 had a bit more power to spare than its twin, making it the safer candidate for testing. The test succeeded, and the full implementation succeeded too. NASA announced the confirmation on August 4th, 2026. The plan now is to apply the same Big Bang procedure to Voyager 1, currently more than 15 billion miles away, where a signal takes over 23 hours just to arrive. Sometime in the coming months. Now here's the part that explains why any of this matters scientifically. Voyager 2 isn't just drifting through empty space out there. It's doing something no other instrument humanity has ever built can do, taking direct measurements from inside the local interstellar medium, the region beyond the heliosphere. And the heliosphere is something worth understanding properly, because it's one of the most important structures in the solar system and one of the least visible. The heliosphere is the vast bubble of particles and magnetic fields generated by the sun. The solar wind, that constant outward stream of charged particles from the sun, inflates this bubble and pushes it outward until its pressure balances against the pressure of the surrounding interstellar medium. The outer edge of this bubble is called the Heliopause. Everything inside it, all 8 planets, the asteroid belt, the Kuiper belt, sits within the sun's bubble. Beyond the Heliopause is interstellar space. And the heliosphere does something critical for life on Earth. It partially shields the solar system from galactic cosmic rays, the extremely high-energy particles that constantly stream through the galaxy from exploding stars, colliding neutron stars, and other violent cosmic events. Without this partial shielding, cosmic ray radiation reaching the inner solar system would be significantly higher. The planets inside the heliosphere exist within a protective structure the sun itself creates and sustains. Understanding how that structure works, how thick and variable it is, and how it interacts with the interstellar medium pressing in from outside is fundamental to understanding how habitable this solar system truly is over astronomical timescales. Voyager 1 crossed the Heliopause on August 25, 2012, at roughly 121 astronomical units from the Sun, where 1 astronomical unit equals the Earth-Sun distance, about 93 million miles. Voyager 2 crossed the Heliopause on November 5, 2018, at about 119 astronomical units, taking a slightly different path that crossed the boundary from a different direction. When Voyager 2 made its crossing, something remarkable happened that hadn't been possible during Voyager 1's crossing. Voyager 1's plasma science instrument had already failed back in 1980, while Voyager 2's was still functioning. So for the first time, humanity had a working plasma instrument capable of directly measuring the plasma environment at the exact moment of Heliopause crossing, and continuing to measure it in interstellar space afterward. The results were full of surprises. At the crossing, Voyager 2 recorded plasma just outside the boundary at roughly 30,000 to 50,000 Kelvin. That's between 30,000 and 50,000 degrees. Scientists hadn't predicted temperatures anywhere close to that in the local interstellar medium at that location. The interstellar medium was expected to be cold, sparse, and quiet. Instead, Voyager 2 found plasma dramatically hotter than the models forecast. The heliosheath, the region just inside the heliopause where solar wind slows before reaching the boundary, also showed a different structure than expected. The termination shock, where solar wind first slows from supersonic to subsonic speed before eventually reaching the heliopause, differed in shape and location from predictions. And the heliopause itself turned out not to be a clean, uniform boundary, but a complex, layered transition zone where properties shift gradually across several distinct regions rather than changing sharply at one line. What Voyager 2 has been detecting since entering interstellar space, and what its 3 remaining instruments are still measuring right now in August 2026, is the actual composition, density, temperature, and magnetic field structure of the space between our solar system and the nearest stars. The magnetometer measures the magnetic field of the interstellar medium, which isn't zero. There is a magnetic field out there, carried by plasma ejected from dying stars over billions of years of galactic history. The plasma wave subsystem detects oscillations in interstellar plasma, letting scientists measure the density of electrons in the medium around the spacecraft. This is the same type of instrument that, on Voyager 1, has continuously detected persistent narrowband plasma wave emissions since 2017, allowing scientists to map the interstellar medium's density across stretches of space as the probe travels through it. The cosmic ray subsystem, the 3rd instrument still running on Voyager 2 thanks to the Big Bang's success, measures galactic cosmic rays arriving from deep space. These outside measurements tell scientists exactly how much shielding the heliosphere provides the solar system, and how that shielding shifts with the solar cycle. The sun goes through roughly 11-year activity cycles. Near solar maximum, when the sun is most active and solar wind is strongest, the heliosphere expands slightly and provides a bit more shielding. Near solar minimum, it contracts slightly. Voyager's instruments in interstellar space can directly measure how cosmic ray flux outside the heliopause changes over time, giving scientists their first outside-in view of how the heliosphere's shielding effectiveness shifts with solar activity. The data is also revealing something about the heliosphere's shape, a subject debated for years. Before Voyager 2's crossing, the standard model assumed the heliosphere had an elongated comet-like shape with a long tail trailing behind it, opposite the direction of the sun's motion through the galaxy. Voyager 1 crossed the heliopause heading roughly north out of the ecliptic plane. Voyager 2 crossed heading roughly south. Both crossings happened at similar distances from the Sun, about 119 to 122 astronomical units, despite occurring in completely different directions, suggesting the heliosphere might be more spherical than older models assumed. But the two crossings also revealed different magnetic field behavior. Voyager 1 recorded dramatic magnetic field fluctuations right at the heliopause. Voyager 2 saw none of that. The heliopause looked structurally different depending on direction, meaning the heliosphere isn't symmetric. Its shape and boundary properties vary depending on where you look. And we currently have only two direct, in situ data points to work from. Every additional day, Voyager 2 keeps operating and transmitting adds another data point to humanity's only direct record of what space outside our solar system actually looks like. The signals coming back from Voyager 2 arrive at Earth's Deep Space Network antennas at extremely low power. The spacecraft's radio transmitter puts out just 23 watts, roughly equivalent to a refrigerator light bulb. By the time that signal has traveled over 13 billion miles to Earth, it's spread across a huge area of sky. The receiving dishes at Deep Space Network facilities in California, Spain, and Australia have to combine their signals just to detect the data stream, which arrives at 160 bits per second, comparable to a 1990s dial-up internet connection. At that rate, transmitting a single modern photo would take hours. Everything Voyager 2 tells us about interstellar space comes through that trickle, and engineers at JPL, some who've worked on this mission for decades, some who weren't even alive when it launched, manage that trickle with extraordinary care, deciding what data to download, when to download it, and how to keep the hardware alive long enough for the next batch. The goal now, following the Big Bang's success, is to keep Voyager 2's three instruments running through at least 2027, and potentially much longer if the hardware holds up. The engineering team has said that if both Voyagers stay healthy, the mission could potentially continue with at least one science instrument into the 2030s. Voyager 1 will also get the Big Bang treatment in the coming months. On November 18, 2026, Voyager 1 is projected to reach exactly 1 light day from Earth, the first human-made object ever to reach that symbolic distance. A message sent from Earth at that moment would take 24 hours to arrive, and another 24 hours for any reply to return, a full 2-day round trip for communication with something built by human hands and still operated by human minds. Voyager 2, meanwhile, won't reach 1 light day until November 2035, and the most realistic engineering estimates suggest it may not still be running by then, though the probe keeps surprising the teams working on it. What's at stake in keeping these instruments alive isn't just data for its own sake. It's the only current direct measurement of the local interstellar medium that exists anywhere. Every other measurement of interstellar space is indirect, gathered by telescopes reading absorption patterns in starlight, or by instruments like the Interstellar Boundary Explorer, which detect energetic neutral atoms streaming back into the solar system from the heliopause. Voyager 2 is physically inside interstellar space, physically surrounded by it, measuring it from within. Nothing else can replace that. No other instrument today is capable of that kind of measurement. The next dedicated interstellar mission, if one is ever funded and launched, would take decades just to reach the distance Voyager 2 has already covered. So the data traveling back along that 19-hour signal path right now is genuinely irreplaceable. Every watt the Big Bang saved isn't just electricity, it's a measurement that couldn't be taken any other way, by any other means, for potentially a generation. A spacecraft that launched 49 years ago, built with early 1970s technology, moving at about 34,000 miles per hour through the space between the stars, is still measuring, still transmitting, still teaching us things about the universe we couldn't learn any other way. And on August 4th, 2026, a team of engineers sent a command that traveled 13 billion miles at the speed of light and came back with the news that it worked. The Big Bang succeeded. Voyager 2 keeps going. The signals from beyond our solar system keep arriving, and the universe past the heliosphere keeps proving stranger and more interesting than the models predicted. That's where Voyager 2 stands right now. That's what it's doing. And because of what happened today, it's going to keep doing it for at least another year.